welcome back. The topic of this video is the interaction of photons with matter. And we can see an example of that if we look behind me, where you'll see the sun is setting, the colors are changing. That's really light, photons, interacting with matter. Of course, the photons that we're concerned with in the medical applications are much higher energy, and not in the EV range, but in the KeV range or MeV range. So we'll look at that. But before I do that, I'm going to start with a little bit of background. I want to talk about different types of therapy, how we use photons, how we use particles, just kind of set the stage, and then we'll get into the discussion of photons interacting with matter. All right, here we go. So I'm going to start with a general introduction here. Here's a patient with a superficial tumor, and this is something we might treat with an electron beam because that deposits dose superficially. Now here's a patient with a more deep-seated tumor, and typically we would treat that with a photon beam because the dose can go in deeper, and we'll study that in a minute. But remember also that some of the photon beam is transmitted, and that's actually used for imaging, and you can measure the attenuation. And then finally we have now a third kind of particle, also for deep-seated tumors, and these are the heavy charged particles, the proton in particular, but also heavier ions that we'll learn more about later, and those deliver dose deeper. Now if you look in here at the photon part of this, what happens on the microscopic scale is the photon comes in, interacts with an electron in some way, and the electron gains some energy or speed. That deposits dose. The photon is scattered off in some direction. So you've got two things going on: scatter of the photon, and that actually changes the energy of that photon, or the photon is fully absorbed in the tissue. And remember, it's the electron doing the dose deposition. So we're going to review now all these interactions, photons with matter. So number one, coherent scattering. And this is a process where the photon comes in, scatters with an electron in some way, and that electron actually moves up and down. And as we'll learn later, a charge moving up and down, accelerating, produces an electromagnetic wave. So there it is. It's got some wavelength lambda, and the wavelength out is equal to the wavelength in. And there are two types: Thomson scattering, that's with a free electron; Rayleigh scattering, that's with electrons that are bound in an atom. So second is photoelectric effect. That happens more prominently at lower energies, diagnostic energy. Compton scattering, higher energy, and pair production at even higher energy. We're going to study all three of these in detail. So let's start with the photoelectric effect. If I zoom in here, you'll see you've got electrons in the orbitals within this atom. And what happens in photoelectric effect is a photon comes in, and it interacts with one of these electrons. Here it's going to interact with this inner shell electron. And that electron then is ejected out of the atom. So the atom is ionized. And that then is called a photoelectron. It's just a special name for an electron that's ejected via this effect. So let's consider the energy of that photoelectron. You can calculate it. First of all, you start out with the fact that the photon has some energy, E gamma, and the electron sitting in the atom has some binding energy, call it EB. So the energy of the photoelectron is going to be the energy coming in, the energy of the photon, minus the binding energy that was required to liberate that electron. Now, of course, if the energy of the photon coming in is less than the binding energy, you won't get anything out. Now let's consider what happens. So the inner shell electron is ejected. So this next shell electron falls down to fill that shell at lower energy. And then in that process, it releases energy in the form of a photon that comes out. Now this is called a characteristic X-ray. And it's characteristic, it's called because it's characteristic of that element. In other words, of the energy level differences in that atom. And so it only happens at specific quantized energies, characteristic. So I'm going to list the things that come out. So in this photoelectric effect, number one, the photoelectron. Number two would be the characteristic X-ray. And then number three is the fact that you have an ionized atom left over after the end of this whole thing. So that's photoelectric effect in its basic steps, but I left out one thing. There's another type of interaction that can happen. This characteristic X-ray, so let's say instead of leaving the atom, it can actually interact with an outer shell electron. Because that outer shell electron is a lower binding energy, it can be ejected. It has enough energy to be ejected. And that electron ejected is called an Auger electron. And it comes out with a specific energy. And some of the problem sets you'll work through, you'll calculate some of those energies of Auger electrons. All right, so now we've talked about how the photoelectric effect works when it does happen, but we haven't talked about how often it happens. And that's important, and so I want to talk about that next. So the way to understand this is to look at this graph, which shows the cross-section for interaction of a photon with the photoelectric effect. You're plotting the y-axis, which is mass absorption coefficient, which is essentially some measure of the probability. We'll learn about it in more detail later. And what you'll see here is that it's really relevant mostly for diagnostic energy. So here below, let's say about 100 keV or so. And you'll see that this falls, and the probability falls like 1 over E cubed until it reaches a certain high energy. And also this is for a particular type of tissue. This happens to be muscle. Now, if you look at another type of material, this curve will look quite different. So let's look here now at the curve for lead. Now, one immediate obvious feature is that it's higher, and that's because the Z of lead is higher. The Z of lead is 82, and what you're seeing here is that the absorption coefficient scales like Z cubed. Okay, so it scales like Z cubed over E cubed. And then the other feature you'll see on here are these edges right here. These are the atomic energy levels, and this is the K shell, the L shell, and the M shell. And you see there's some structure in here because there are multiple levels. And so the concept here is that if you're above the energy needed to ionize an electron from that K shell, then you'll get an interaction. So the probability is relatively high when the energy exceeds the K shell. As you drop below the K shell energy, the probability goes down because you're not able to ionize that atom anymore. So these are characteristic energies, and they're characteristic of that particular element. They can be even used diagnostically. So let's look at another curve. This curve in the middle here is actually the curve for bone. And you'll see it's in between the two. And that's because the effective Z of bone is actually 12.3 approximately. That's, you take the average of all the elements in bone. And so you'll see it goes up. Remember, it goes like Z cubed. The effective Z of muscle is 7.6. And the effective Z of bone is 12. And the Z of lead is 82. So there's that scaling going up with Z. But this 1 over E cubed still is in effect. Also, you'll see on the bone that you can actually see some K shell edges or L shell edges, and those are from the calcium in the bone. So let's look at these three curves again and just talk about the interpretation for a minute in terms of a clinical application. So first of all, concentrating in the diagnostic imaging range, so let's say below about 100 keV, as you go to lower energies, and you can control the energy of the X-ray source, as you go to lower energies, the absorption is going to be higher, okay? And actually the contrast is going to be higher. You're going to be able to distinguish better between the bone and the muscle. The dose to the patient is going to be a little higher too. As you go to higher Z, the absorption is going to be higher. So it attenuates more in bone than it does in muscle. So the contrast essentially is better with lower kVp. The bones are clearly seen, for example, and tissues are more distinguished. When we go to therapy energies, up above, up near 1 or a few MeV, the photoelectric effect is unlikely here, and all these curves are essentially the same at that energy. And really the only kind of area you might think about photoelectric effect in that regime is for high Z elements, for example, tungsten that's used in collimators and so on. All right, that concludes this video, which was about the interaction of low energy photons with matter. Low energy being, let's say, 100 keV or lower, where photoelectric effect, Rayleigh scattering, and so on dominate. I'm going to leave you with a little bit of reading where you can look more in detail at the physics of this. It can get quite complicated. And then in the next video, we are going to go over the interaction of higher energy photons with matter. And that's a regime where Compton scattering and pair production dominate. So we'll see you in the next video.